Alright, so I want to see what the behavior of an induction cooktop is when it's introduced to a bunch of different materials and also to low frequency RFID equipment. Now a lot of these induction cooktops operate around, I think it's between like 200 kilohertz and 600 kilohertz, somewhere in that range. So even though the RFID equipment is not attuned to that frequency, it's pretty close. So you're going to get some kind of interaction. Now I want to see if that's a problem. So to get one of these working, they have foreign object detection to basically detect if there's a load. So I'm going to need to use a cast iron pan to get it going. If I just turn it on straight, it gives me an error. There's nothing here. But if I put this pan on here, it starts to heat up pretty immediately. Now let's see what happens with just a bare piece of aluminum foil, approximately the size of the new flex implants. I want to see if the induction cooktop will induce eddy currents in the foil. It really doesn't seem to be doing anything. Any heat I'm experiencing is from my fingers or from the actual pan itself. So let me try a folded up slightly thicker. I can definitely tell that it's running out to, I mean, basically a foot from the center point, because I have a magnet implant and I can detect the vibrations. Yeah, not getting any eddy currents in this aluminum. How about I try a much bigger piece of machined aluminum. I'm just going to leave that on there while we're doing the rest of our testing, because it's going to take a minute. So, as you've probably seen online, these things work really well with coils. So I made a little coil foil coil. So let's try that. So I can definitely feel that the field is present. And I'm pressing the center point of the aluminum to the outer point to see if I can get some kind of current flow. Now aluminum foil is really thin, so this idea probably won't work, and I'm not feeling any heat being induced. But I could try a copper coil. So this is a 3D printed coil form with just a bunch of pieces, windings of copper around it. I was using this from some experiments, so it's going to be useful for this. So I've got this held together to create a current pathway. So this pan's getting pretty hot, but I'm not noticing any current being induced in this thing. So let's try this coil. Is a complete circuit, and it has an LED as a load. So this is a ferrite center. Oh my god, look at that! Did you see the green? Ah. So that's very interesting. So it's basically a wireless charger for low frequency. Very interesting. Well, doesn't bode well for our low frequency implants. So let's try an even smaller form factor. Let's try a little XLED. This is actually the field detector, so it's made of lower quality materials, but the circuit's very similar. Oh, and this is vibrating in the casing. Now, it's getting pretty hot in here, and this pan is well treated, so it's got a bunch of crap on it. Let me open a window. Some birds up in here. So I'm not getting any lighting up with this tiny implant coil, although it is getting pretty hot. So let's try with this T557, the Flex EM. Let me get this near here. So the pan itself is very hot, but I'm not experiencing any heat induction into this implant or this aluminum block at all. So aluminum might not cooperate with this. It doesn't have enough of a magnetic field. We did see some activity from the low frequency, basically tuning fork, but this implant is not getting any measurable temperature increase. And I expected if it did, it would happen immediately. So this prolonged exposure bodes well. I think that these implants will be okay. There's not a lot of actual material in here. And as we checked earlier, just straight copper doesn't quite do it. It's only really ferromagnetic materials like this iron. So we'll probably be okay.